you have all of them are using a sinusoidal message. But one's beta 2, then there's one for beta 5 and one for beta 10. So let's do the beta 2 one most of the way so you can see how it's done. Let me rewrite this now. So FM signal is a function of time. A sub c sum over n. Our Bessel function, cosine carrier frequency plus integer multiple of message frequency with time. We're given some things here. We're saying let a sub c equals 1 for simplification problem, then it just drops out. Carrier frequency is 250k, so 2 pi times 250,000. Message frequency is 10k, so 2 pi times 10,000. And for ours, part A, beta is 2. So let's write this out with those substitutions. FM signal as a function of time is equal to, all right, A sub c is 1, so we don't see it anymore. Jn of 2, because our beta is 2, cosine 2 pi times 250, I'm just going to say k instead of 1,000 to save space, plus n times 10,000 t. All right, so there's we've specialized it for our beta 2 case and for those frequencies. Now we just start cranking. Let's start with the n equals 0 term. We're after the spectrum of this thing. If we've got a bunch of sinusoids, you can see why the spectrum is a bunch of spikes. All right, if I say J0 of 2, by the way, probably now is a good time to talk about the Bessel function before I launch into that problem. So Jn of beta, his official name is the Bessel function of the first kind, order n, argument beta. So there's the official title. If you're going to go get it off MATLAB, it'll probably say something like Bessel function of the first kind, and it'll be the right one. And you can test it out by doing some of the numbers I'm going to give you, make sure they match before you just go with it. If you're going to do it on your calculator, which what I chose to do, here's the equation that you use for numerical integration. 1 over pi integrate 0 to pi, cosine beta sine x minus nx dx. So there's the equation, for Jn beta that you can use I just plugged it in, did it on my TI calculator like 20 years ago when I first started teaching this class. And if it worked 20 years ago, I'm sure what you got now will work. Probably got way better than that. So there's the equation that you can use and integrate numerically with respect to x. Plug in, the beta value, plug in a particular n value, so you'll have to do this over and over again for every n. Maybe you could numerically integrate it on MATLAB if you didn't want to use their Bessel, whatever. There's different ways you can do it. So when I crank out that equation for n equals 0, beta equals 2, here's what I get. 0.2239 is the weight I got from the Bessel function. Cosine 2 pi times 250,000 plus, n is 0, there is no plus anything, t, so there's our first term. And you can see this is just a carrier frequency cosine. What's the spectrum going to be? We know this. We're good at this now. Double spikes, plus or minus 250K. That divided by 2 in amplitude, right? I'll wait to plot all this till the end. Let's get all the terms carried out. So this is our n equals 0 term. All right, plus, all right, so now this is going to be our n equals 1 term. All right, so if I say J1 of 2, I get 0.5767. So these numbers right here, they're the ones before you go running off with a MATLAB Bessel. Make sure you're getting these numbers. Otherwise you got the wrong Bessel, okay? If you choose to use MATLAB. All right, so this times cosine 2 pi times 250,000 plus, okay, n is equal to 1 now, so it's plus 2 pi times 10k t. All right. Now it turns out that at least the absolute value, not necessarily the sign, but the absolute value at least of this is going to also be what we have for n equals minus 1. So let's just include that here. Same constant, at least in value. Let's see, for n equals 1, it's going to be minus here in this time. Cosine 2 pi times 250,000 minus n equals 1, minus 1, so it's minus 2 pi times 10,000 t. So this is our n equals minus 1 term in curly bracket. So here we have a sinusoid that's 260,000 and 240,000. Double spikes. Amplitude that over 2. All right, let's keep going here. N equals 2. For n equals 2, I get plus 0.3528 for my J2 of beta, equals beta's 2 as well. J2 of 2, cosine 2 pi times 250,000 plus, okay, now 2 times 10k, so 2 pi times 20k t. So this is our n equals 2 term. Now for the n equals minus 2 term, I get, it's going to be plus, not minus this time, cosine 2 pi times 250,000 minus 2 pi times 20k. So there's our plus or minus 2 terms. You see how this is working. Now we've got a 230 kilohertz sinusoid and a 270 kilohertz sinusoid. All right, let's go to n equals 3. Let's see if I can squeeze it in here. For n equals plus 3, I get plus 0.1289 for my Bessel weight. Cosine 2 pi times 250,000. So this is our n equals 3 term. Plus 2 pi times 30k. And for the n equals minus 3, let's see, for this one, the minus 3 ends up being a minus this time here. Cosine 2 pi times 250,000 minus 2 pi 30k t. See the pattern emerging here. It's not that hard. It's not very difficult. Let's do one more. You guys will have to do a little more at home, but I'm getting tired of this. As probably are you. Alright, the last one I get is, let's see, that was 3, so this is n equals 4 term. For n equals plus 4 term, I get 0.0340 cosine 2 pi times 250,000 plus, now it's going to be 4 times, so it's going to be plus 2 pi times 40 kilohertz t. Now the n equals minus 4 term. For minus 4, it's a plus this time. Cosine 2 pi 250,000 minus 2 pi 40k t. And so on, forever. So we'll stop there and plot this. There's 200k, the carrier. Here's minus 200k. All right, so our first job is to do this first term, just pure carrier. So that divided by 2, spikes plus or minus 250. I said 200. 250. So it's going to be 0.11195. There's our carrier cosine, double spikes, 0.11195. There's our first term, pure carrier. All right, now we've got 260 and a 240. Amplitude that over 2. 2.88 I get, so 260k, 240k, minus 240, minus 260. And the height is more than double the other one, so 2.88, and something like this. Same over here. So these spikes right here are the 240 cosine, and these outer spikes, the higher frequency ones, are the 260 sinusoid. Double spikes, plus or minus, whatever the frequency is, amplitude, that chopped in half. All right, so there's the n equals 1 and minus 1 terms. Let's go to the other one. So this is going to be at 270 and 230. That over 2 in amplitude. 270, 230, minus 230, minus 270, and I get 0.1764, so something like this. Alright. 280, 220, that over 2, 280, 220, height 0.064 or something like that. Now we're getting pretty low. As we would expect for a beta 2, we wouldn't expect the spectrum to be that wide in bandwidth. Our beta 10 case is going to be wider, isn't it? We would expect that. All right, last one. So now we've got 290 and 210. I've almost done the whole thing for you. Let's see, it's going to be 0.015 something or other. So you see it's symmetric about 0 and also symmetric about the carrier. So I'm fine, honestly, if you just do the right side and say, and this is also repeated down there, the mirror image at minus 250. This is all we'll see on the spectrum analyzers when we do this lab. I calculate, I think like I said last week, that this is going to be the first lab we actually can include this data in our report. I believe I'm correct about that. And it's a good one because if you do this properly, it's pretty good percent error numbers on this.
So how far did you want us to go, the harmonics?
Yeah, let's agree on that right now. So this one right here, I almost did the whole thing. Let's say for the beta equals 2 and 5, we want to go, let's go over this range here let's go 200 kilohertz to 300 kilohertz. So I almost finished it for you. For the beta equals 10, we're going to go wider, like 140 kilohertz to 360 kilohertz. Let me double check that. I think that's right. Yeah. So make sure you go wide enough on the pre-lab. And I've done this one mostly for you so you know you're doing it right, you got the right vessel and all that stuff. So what does this mean? When you look at a spectrum like this, what does it mean? Or if you look at it, what it's saying in math over here. This is telling us that if we have this picture, that now it's like the third time I've drawn it, but let's draw it again. If you have a sinusoid message, and you have a FM modulated, version of that message, what this is telling us here is that I can make this up by adding together a bunch of sines and cosines, well, it's a bunch of cosines here, a bunch of cosines of different amplitude and frequency. If I add all these up, they'll add together and they'll be that. And this is just saying it in the frequency domain. If I add all these different sinusoids together, I'm going to get that. This is what this signal is composed of. The sum of a bunch of sinusoids.
So that's like a Fourier series?
It is like it is. It's very much like the Fourier stuff, where we do the same thing, but there it's all the same frequency, isn't it? So this is different here, and that's where Bessel comes in. But it's telling us the same thing. Now, this is a pretty simple message. We can't really get much more simple than that. And look at all the complications. Imagine if we had a complicated signal like voice or something. Forget even trying to do it in math. Ain't gonna happen. Very complicated. I mean, all this just to add together to make a simple, oscillating type of infrequency. Imagine if it was a complicated signal. It's just beyond our ability to do the math and to make it, something that is doable. So you have to resort to, your electronics just does it, just does it in a completely different way than this. But this is hard enough here. You could probably resort to some statistical techniques to do it, like from your stochastic processes class. But you can see how it's complicated. So you should be good now to do pre-lab, the FM pre-lab. There's also a second part that says make an FM demodulator from a few simple things like in the lab. And that's where you get to go and kind of do a little research in your comm book or online for easy FM demodulators. Just do your best. The only way that you can lose points on it is if you just don't do it at all. But if you try, you'll get the points, even if it's maybe wrong. Okay? So at least give it a go and try to research on how you would make a simple FM demodulator. Questions before we go and leave FM and talk about tonight's lab?